symmetry in platonic polyhedron.
Abstract. Symmetry problem is a type of combinatorial optimization which has practical application, such as finding the certain total length of wires needed to join given number of points. By far, most of the research on the spinal trees are planar, and therefore we are interested in exploring three-dimensional spinal trees. Introduction. In triangle ABC, we want to find points S such that the sum of the distance of segment SN, segment SB, and segment SC is shortest. So we can call point S is Fermat's point. Second, in a convex polygon, we want to add some points. We want to add some points S1, S2, such that the sum of the distance to point S1, S2, etc. that we added is shortest. So we can call point S1, S2 is a final point, and the dark blue path is spinal trees. This is our research equation.
Thank you, amazing. In our study, we start from the standard tree of regular polygon, and then generalize the standard tree of platonic polyhedron. Now we are going to introduce the planar graph and the method of triangle. There are two cases of triangle. First one is the largest angle is less than 120 degrees, and the second one is the largest angle is not less than 120 degrees. And in our research, we only use the first case. And the method is we choose segment AB and segment AC to make equilateral triangles. Then we connect segment QC and segment BS, which intersect at point P. So point P is the main point of triangle. And the standard tree of square. We choose segment AD and segment BC to make equilateral triangle and circumcircles. Then connect segment EF, which intersects at S1, S2. And in the other hand, we choose point G as the gravity of triangle. Then we consider triangle ADG and triangle CGB. Then make the Fermat point of these two yellow triangles, S1 and S2. And they are the standard point of square. And then in rectangle, we choose the shorter side to make equilateral triangles and circumcircles. Then S1 and S2 are the standard points of rectangle.
Now we're talking about platonic polyhedron. Next we'll introduce the spinal tree of tetrahedron. There are 4 faces, 4 vertices, and 6 edges in tetrahedron. By former experience, we use in square. We consider about triangle GAB and the triangle GCD. We find the spinal point is S1, S2. Then the red path is spinal trees of tetrahedron. Next, we'll check the bubble form film model. We made a couple wire model with each side is 10 cm and another one is 20 cm. We put it into bubble water, pour it up with vertically and 45 degrees repeatedly. There are only one knot inside. By symmetric properties, we consider a knot is gravity of tetrahedron. Then we found the distance is more than we had mathematics. We figure out that the bubble form is minimum test and the minimum energy structure. In 2010 American Journal of Physics, we want to find something to explain why the bubble form is not the minimum path.
the standard tree of hexahedron. First, we make a standard tree of square, then move it into the center of hexahedron. Then we consider these 4 rectangles. We make the standard tree and the center point of these 4 rectangles, and rotate S1 to SA, rotate S2 to SB, rotate S3 to SC, and rotate S4 to SD. Then we found when the 4 rotate angles are equal 15 degrees, then the broad edges will match the pink edges. So there are 6 standard points in a hexahedron, and the red edges are the standard trees. And in Barbosa's experiment, we found there are 4 nodes in the hexahedron. By calculus, we can find the minima length, which is larger than the length we found in mathematics.
Next, we'll introduce the octahedron. There are 8 faces, 6 vertices, and 12 edges in octahedron. The 12 edges happen to be the edges of 3 squares. Each square have 2, so we have 6 standard points. These 6 points just be vertices of hexagon after calculation. By inner product, we know each point connect the adjacent vertices of octahedron is 120 degrees. And the graph is exactly the Barbosa form of the octahedron. But by our former experience, it should be 2 points, less than vertices of polyhedron. That is, there are 4 standard points in an octahedron, so we want to remove 2 of them. And there is no cycle, so we remove the path connected repeatedly, the vertices of octahedron. Remove the path with cos cycle. Finally, we remove 2 points, which is the symmetrical to the centroid of octahedron, and connect the tree. Now we'll have the standard tree of the octahedron, which has 4 standard points and 9 edges. Then we make a mathematical model and find the shorter path than we had. Then we prove it in calculus. The simulation result match the proof. We show the proof on the test.
Now we are going to introduce the standard tree of dodecahedron. There are 12 faces and 20 vertices, and 8 of vertices form a hexahedron, and other 12 vertices form 3 golden rectangles. And we have 2 methods. Method 1, we consider a hexahedron, and a hexahedron has 6 standard points. Then we divide the dodecahedron to 6 same parts and a hexahedron. Then we connect the red edges. So this is the standard tree of method 1. And method 2, we consider the 3 golden rectangles. Each rectangle has 2 standard points. So there are 6 standard points, which form an octahedron. Then an octahedron has 4 standard points. Then we connect the tree. And we found there are only 10 standard points. By our former experience, dodecahedron has 20 vertices, so it should have 18 standard points. So we choose the middle point of red edges. So there are 18 standard points of the dodecahedron.
Next, we'll introduce the octahedron. There are 20 faces, 12 vertices, and 30 edges in an octahedron. The 12 edges is exactly the vertices of 3 golden rectangles. Each rectangle has 2 final points. So we have 6 final points. So, which is the vertices of an octahedron? By former experience, we know that there are 4 spinal points in octahedron. So we have 10 spinal points. Then we connect the red hat. This is spinal trees. In the same way, we use straight bar to make simulation and the final result match our proof.
Result and discussion. We show our research on this table. And in our research, we verify the mathematical model and the bubble solving. And we prove the minimum pace of octahedron and dodecahedron. And our paces are shorter than other research we found. And we prove the minimum pace of hexahedron that no other report mentioned about it. And in bubble source experience, we found tetrahedron, hexahedron, and octahedron are longer than the standard tree in mathematics. Although the form of bubble source was the shortest on the pen, whether it remains the shortest measure of area on a curved surface in the 3-dimensional space is worthy for further discussion. And in our conclusion, we use mathematical software GeoGebra to find the standard tree of platonic polyhedron. And finally, we prove from the standard tree of planar convex n-gon to 3 dimensions. And in 2 dimensions, the number of vertices of a regular polygon is phi, and the number of standard points is s. Then we have a rule of s equal phi minus 2. And in 3 dimensions, the number of vertices of a platonic polyhedron is phi, and the number of standard points is s. And suppose s equal phi minus 2 also holds, then we prove the minimum pace we found. And in our future prospects, we know that the structure of adenovirus is an hexahedron, and the standard tree has the minimum energy. If we can destroy the structure, maybe we can kill the viruses. And there are lots of sculptures of therefore use the polygon structure. And how can we spend less money and have a stable structure? We can consider the standard tree in our research. And this is our reference. Thanks for listening.